Welcome to today's webinar, Anticipating the Impact of Fusion for Energy. It'll be featuring an interview of Dr. Axel Meesen. This will be the first of two webinars. The first one we'll be looking at, so what is fusion anyway, and also anticipating its implications or its impact. The second webinar, which will come at another date, we'll be addressing some of the regulatory matters and recommendations on what we need to do to prepare. My relationship with Dr. Meesen goes back maybe too many years, but you were president of Memorial University. I think it was the work that I was doing with the Alberta Council of Technologies that brought us together. And in fact, I think my initial introduction to you was really through Barbara, your wife.
Mm-hmm.
In any case, after that, I think it was Foresight at Alberta Innovates that you were champion of for some years, which was looking at technologies. And I can remember you doing a Sterling session for us about the ramifications of energy and weaponizing energy on a world scale as we looked at the future economy. And then more recently, of course, the president of Fusion Energy Council of Canada, which is the role that you play now. So have I missed anything regarding what you might want to share with the audience as an engineer and as someone always interested in technology and its implications?
No, I think you've covered the important parts. You might add that I now reside in British Columbia, but I have not lost my interest in matters Albertan or matters Newfoundland and Labradorian for sure.
Yes.
So,
well, I can see out the window to the side there that you're in a little bit different territory than we are here in Alberta.
yes.
Okay, well, let's pose the first question. How would you explain fusion energy to someone that's unfamiliar with the science behind it?
Well, it's not that easy to explain, but let me try and do it by drawing attention to the fact that fusion energy is produced in all of the stars, including our sun. So let's take a look at what's happening in the sun. The sun is very hot, about 10 million degrees or thereabouts. And that means that the constituents of the sun are in a state which is called the plasma state. Now, the constituents of the sun are principally hydrogen and helium. Together, they amount to about 98%, 25% helium, 73% hydrogen, and the rest are some other small constituents. At these very high temperatures, the nuclei of the atoms move extraordinarily rapidly, so that in the case of hydrogen, they move at almost a million meters per second. And even though the nuclei of the atoms are positively charged and therefore do not like to interact, the speed is high enough that under certain circumstances, they can impinge and they can then fuse. The second thing that must happen is, of course, there has to be an opportunity for them to collide. And because the gravitational force in the sun is about 28 times that on Earth, the density of the sun is high, which brings about frequent collisions. And the third factor that you need is time, because it's a probabilistic event for atoms to collide. So you have got these three factors, temperature, which is related to the speed of the nuclei, density, and time. And that's what's known as a triple product. You have to have the combination of all three, and that triple product has to be above a certain limit. And that's what we try to achieve on Earth. And you can imagine it's very difficult to get temperatures in excess of 10 million degrees, or to get densities that are comparable, if not higher than what's in the sun. But that's exactly what we're trying to achieve. And we're getting pretty close to doing that. And we have demonstrated it in a number of occasions. Now, when the collisions and the fusion of these hydrogen nuclei occurs, there is helium formed, and that helium has a smaller mass than the nuclei of the hydrogen. And that results in the conversion of mass into energy And many of us are familiar with the Einstein's equation of energy is equal to mass times the square of the velocity of light. So it releases a very large amount of energy. So think about the sun, our sun, in connection with fusion energy production. And we're trying to replicate basically what is happening in the sun, although we're not using the same constituents as we will discuss later on.
So you've explained it well. I think I understand the relevance of density, time, and speed. And you've also indicated this is somewhat complex. I understand the science is there. The engineering is another matter. Why is fusion energy considered a game changer? I mean, if we have the capability of producing energy through fusion, it's going to make a difference in the energy sector compared with fission, which is also nuclear, solar, and wind. This could be a game changer. I don't know whether it's imminent or not. It's interesting in textbooks, but why do we refer to this as a game changer?
Well, people refer to it as a game changer because the amounts of energy that you can produce from very small amounts of starting materials are enormous. So let me give you some figures to illustrate that. In order to produce a gigawatt of electricity for a year, and a gigawatt is the typical energy requirement of about 1 million homes.
Wow.
in Alberta or in Canada. To do that, you would need theoretically something like 90 kilograms of deuterium and 270 kilograms of lithium per year. In a larger electric vehicle, you have more than 270 kilograms of lithium. So that's not a very large amount. And 90 kilograms of deuterium is not a very large amount either, because deuterium occurs naturally in all types of waters, saline waters, fresh waters, and it can be extracted from there. So you need very little starting materials in order to produce very large amounts of energy, and that's attractive. The other reason why it is attractive is that it is not directly associated with any greenhouse gas emissions, because the conversion of deuterium and tritium, that are the tritium comes from lithium, which are the favored input materials, only results in helium as the final end product. Some people refer to it as an ashole, even though helium is a gas, as we all know from birthday parties and other occasions.
So deuterium, tritium, lithium, these are things derived from seawater, of which we've got plenty. Some say we'd have a billion-year supply or almost an infinite supply of energy in terms of the inputs. And the outputs, as you mentioned, are helium. There's some radioactivity, I gather.
Right.
This is something we haven't talked about at length, but I gather there is some radioactivity in what other vessel or how you produce this. Is that a significant concern? Because that's often been one of the drawbacks of fission.
Yes.
Or,
Yes. Yes, it is. The radioactivity results primarily from the fact that when deuterium and tritium fuse, they produce neutrons, and it's these neutrons that have very high energies, and they can induce radioactivity in certain types of metals, like iron, which is you find in steel. And these radioactive materials that are produced in that way have a half-life of less than about 100 years, but that's very much less than the typical radioactive products that one gets from fission reactors, but it's not inconsequential, and one needs to think about that. And I should point out that the tritium is really an intermediate product. that you make from the interaction of neutrons with lithium. And tritium is also a radioactive product. It has a half-life of about 12 years, and you wouldn't want to ingest it, although its radioactivity is low, but it really has to be managed well. And so there are radioactive considerations, at least with respect to the deuterium, tritium, lithium approach to fusion. There are other reactions that one can look at that have less radioactivity associated with them, but they require even more extreme conditions than what the deuterium, tritium fusion production requires.
So the world's current anxiety is about the production of carbon dioxide. You haven't mentioned that, I don't think, at all. So we're talking about a source of energy that if climate change is your anxiety and the production of greenhouse gas emissions is your concern, we have here what some might refer to as the holy grail. That's really where the game changer is given current anxiety about the climate. We have something that is essentially free from any of these considerations. So, but what advances are we making? It's all well and good to talk about fusion energy and sun in a bottle on Earth, but are we really making any headway? It was always 50 years into the future. Where are we? What advances have been made of late that have brought this back into mainstream discussions?
Yes, let me comment on this, but let me also say in all fairness, while the fusion process does not produce greenhouse gases, there are, of course, greenhouse gas emissions from the production of the hardware, the facilities, and one should not overlook those. And those of us who work in the fusion area recognize that, and we are fully aware that there has to be total accounting of all the greenhouse gas emissions, not just from the plant, but also to make the plant and ultimately to decommission the plant.
There's obviously some energy required to construct the plants, to deliver the inputs.
Right.
So we're not naive to the fact that we're not
Right.
getting rid of fossil fuels, for example, overnight or maybe ever. But let's get back to the commercial opportunities. Are we getting closer to the point where?
Okay, so where are we at? Apart from the fact that we know that fusion does occur in all the stars, so it's not an imaginary phenomenon, but to do it in under industrial conditions or in the lab is quite something different. So for the first time in late 2022, at the National Ignition Facility at Lawrence Livermore in California, it was demonstrated that you can fuse deuterium and tritium in very small quantities with a net energy production. And the way it was done is a small pellet of liquid deuterium and tritium was irradiated by a set of 192 laser beams. They imploded and they fused, and as a result, energy was released. However, this is just the energy that was produced as deuterium and tritium were fused. It did not account the amount of energy that you needed in order to produce the laser light, for example, and all the other things that surrounded it. So the real challenge is now to take these scientific experiments and their results and to scale them up. And that's a big challenge. Some people have used the analogy of the Wright brothers' first flight in 1903 or thereabouts, which was maybe 100 meters and a little bit more than that. And what looked like a pretty rickety aircraft, but it did fly. And look at what has happened in the course of 100 years, where that initial experiment and that initial demonstration has taken the aviation industry today. So I think many of us anticipate something similar, but there has to be a real demand for the product, and the product, which is energy, has to be available at a cost that is affordable. And to get there with a complicated process is a big engineering challenge, just like it was to build an aircraft based on the very simple concept that the Wright brothers demonstrated at the beginning of the last century.
So that's where, and I refer to the dawn of fusion, is we're at that dawn. We visited Kitty Hawk, that was Livermore.
Yes, yes.
The interesting correlation was that breakthrough at Livermore was almost simultaneous with the announcement of the learning language models, now ChatGPT, and the advancement of artificial intelligence, which is sweeping the earth. And I suspect the day that fusion is commercially viable, we're going to be at a similar stage. And I'm now seeing billions of dollars being invested in fusion at the commercial level. So we've moved beyond simply government's involvement with Livermore into the commercial sector. But we'll get into that in a moment. I'd like to know about this usage of fusion energy to produce electricity. It's all well and good to have the plant creating heat, but where do we get electricity out of this, and what are the costs likely to look like for the consumer?
It's hard to say what they will look like. It's much easier to say what they must look like.
Okay.
If electricity is available from fusion plants at a cost of approximately 10 cents per kilowatt hour, that would be competitive. We within the Fusion Energy Council of Canada have said we should aim for 1 cent per kilowatt hour in order to make it not only competitive, but to make it widely accepted for consumers and for industry. And you have to couple it with the capital cost of the plant. And again, within the Fusion Energy Council of Canada, we've suggested that the capital cost of a plant that produces about a gigawatt of electricity should be in the range of $1 billion. And the cost to the consumer, the levelized cost of electricity, should be of the order of 1 cent per kilowatt hour. Now that's a should. That doesn't mean we will get there. Certainly the first plants will not meet those two requirements. And our friends in the industry that are closely associated with it have said, if the plant costs $10 billion, that's perfectly okay at a gigawatt output for the first number of plants. And if the cost of electricity is 20 cents per kilowatt hour, that's also acceptable as a first set of plants. But in the longer term, we need to get to much lower costs on both capital as well as operating expenses.
So it's the heat from the from fusion that is converted ultimately into steam, ultimately powering generators that produce the electricity, which may be stored in batteries for our cars, which may be at the outlet of our homes. We don't need a new infrastructure. But I live in Alberta. This has been I hesitate calling it paradise, but in some ways we live on a bit of an island. We're an energy producer. I'm not quite so sure how happy Alberta would be when fusion emerges, but we're not the only energy market. I mean, you've got everything from Nigeria to Russia to Venezuela that are also oil producers and energy generators. Quebec with hydro. What's the impact on the existing energy markets, particularly fossil fuels, and the companies that today dominate them?
I think in the mid to long term, the impact will be profound. But that doesn't mean that the impact is bad. It just means that the impact is going to be major. Let me give you an analogy, which is a little different from the aviation one. Let's look at trains. At the beginning of the last century, most passenger travel was by train over mid to longer term distances. Today, there is virtually no passenger travel over mid to long distances by trains. But the trains today and the companies that run the trains are dedicated to cargo or to freight. And if you look at CN, CP, and their derivatives in Canada, they are very viable companies today, but they're in a different kind of business from where they were before, namely carrying cargo as opposed to predominantly passengers, because the passengers have to a large extent moved to automobiles, personal automobiles, and for mid and long distances, of course, aviation. So I think what's important for Alberta is, and I've said this many times before, is to recognize that Alberta has hydrocarbons in the form of fossil hydrocarbons that are currently being used to a large extent to make energy products. But in the future, I think there are good opportunities to make products other than energy products. May they be construction materials, may they be textiles, may they be other types of consumer products. Now, they will be, in all likelihood, produced in smaller quantities and requiring less oil and gas than what we are currently producing, but the values will be higher if we do it right. So a really key question for us is to think about what are the products of the future that could be made from our hydrocarbons, other than or in addition to energy products. And the changeover will not be rapid. We're talking several decades.
There are certainly people today that are concerned with pollution and certain products that
Sure.
and one of them was people looking at fossil fuels as a pollutant, and what we're talking about is other usages as lubricants or in plastics or whatever. And that may help Alberta make its transition. By the way, I think you were involved in some research that was looking not so much at electricity, but at the heat that's generated by fusion and the ramifications in the midterm for our oil sands that use heat in production. So there's another positive in that interim that would extend the life and the productivity and the cost, I guess, of the oil sands. But let's move on. I'd like to look at what the world needs to do if we get fusion coming to Canada. There's going to be implications on jobs, not just losses, but the transition to new ones. There'll be new industries, and the cost and availability of energy will be impacted. So we've addressed that to some extent. I'm going to ask what should governments and industries be doing today to ensure the transition? And so often we get excited about a new technology, we jump into it, and before you know it, we've got a whole bunch of not in my backyard players because we haven't anticipated and we're not ready to orchestrate a transition, and then it holds off. So for 25 years we do nothing but complain. What could we or should we be doing now?
What Canada really does need, and we within the Fusion Energy Council of Canada and many others have also said that we need a strategy with respect to the development of fusion energy in Canada, and a strategy that includes the utilization of fusion energy in Canada. So I think it's both to create the fusion energy and to make use of it. And these two things, I think, should be viewed as going hand in hand. We do have some remarkable advances in Canada with respect to fusion energy development. I draw attention to the company that's called General Fusion and located in Vancouver. It has a technology in the early stages to produce fusion energy, which is different from the way that technologies are being pursued in most other countries. But there's an example of a company that has now been in the development of fusion energy for well over 10 years, approaching 20 years with a new technology. But we do not have in Canada, either at the federal or at the provincial level, a strategy that says these are the things we need to think about with respect to fusion. These are the objectives. This is how we can attain the objectives. We've created some of the foundations. For example, Canadian Nuclear Laboratories has produced a very good report early on in 2024 that provides excellent background information on how Canada might go about developing its fusion industry. But it's not a strategy document. It doesn't say these are the things that we will achieve. Here are the resources that are needed. Here are the organizational, the management structures in order to make it happen. And Canada is the only G7 country without a fusion energy strategy, which is noteworthy, and we can bemoan it, but let's make the best of it by saying let's now utilize the learnings from the other countries that have had fusion strategies, and let's build a fusion strategy for Canada that is in keeping with our characteristics and in keeping with our objectives.
As you know, and I think at this point we've touched on the relevance of fusion and the possibility of this becoming that holy grail in energy. And as you well know, I'm as excited as anyone about this technology, but I'm also well aware of how often there are disruptive implications that haven't been anticipated, and we get all these positives being talked about, and nobody was ready. Doesn't this ultimately have some impact on the geopolitical relationships of nations to one another when energy is such a significant element in our politics today? What happens to the geopolitics? And this hasn't been talked about. I'm not sure where anybody is talking about the geopolitics of energy in the future when fusion arrives. Let's weigh into that today.
By all means, let's do that. But there are also similar issues in our own country because we have provinces that are producers of energy. Fusion energy will become, in all likelihood, available. And when it becomes available on a global scale, we will have to adjust to it. And we can either be a participant in its development or we can be a taker. Will it create major geopolitical tensions as well as benefits? Yes, the major oil producing countries, if you think about OPEC, will be negatively affected if electric vehicles and other forms of electricity production become dominant. So that part is clear. However, it's also clear that you can collaborate. And the development of fusion energy is really an international collaborative effort. There's virtually no country that says we can do it by ourselves, although some countries, China, the United States, to name just two, are really determined to do it. But they do want to do it in collaboration because there are too many challenges that any one country can solve and address. So fusion energy development is an opportunity for collaboration. And I draw your attention to something quite specific. In 2025, Canada has the presidency of the G7, and the G7 group of nations and its leaders decided in 2024 that there should be a working group on fusion energy, recognizing the importance of fusion energy to all G7 countries. And I should add that the EU is also part of the G7 group. It's profound, and it's an opportunity for collaboration. So I think fusion energy development, which is a peaceful pursuit, has the possibility of strengthening collaborations between nations. Just because it has the potential doesn't mean it will happen, but the opportunity and I think the will is really there.
So the collaboration can be driven in some people's minds because of the cost. I'm very much concerned on whether or not that collaboration is also looking at the socioeconomic implications so they can be mitigated, and the haves and the have-nots, which is called disparity, is somehow muted. is the issue of socioeconomic implications at all of interest to this collaborative?
Very much so. And one aspect of that is a concern about greenhouse gas emissions, which is a common concern for many. But a very common concern is also the necessity to provide energy at an affordable price. There's still over 2 billion people in the world who have no connection to electricity. And if you ever think about a disparity, that's one of them. What we're going to see, and you mentioned it early on, is ChatGPT and artificial intelligence. Everything we know suggests that that will demand large amounts of electricity and in turn large amounts of energy. And what we don't want to do is disadvantage any groups of people or any nations for that matter.
Okay, well, this is a good point to wrap up then. I mean, in summary, anyone who is not aware of what fusion is has a better understanding and a sense that it's imminent. I can't say short term, but there has significant progress is being made, so it's not purely in the public sector. Industries are now participating. Billions of dollars are flowing into the industry. Tension is building between nations to the point that collaboration is being talked about, not just for cost, but to mitigate climate change implications, and also to address the potential of some significant disparities, or the winners and losers may flip. The winners today are fossil fuel producers. They may be the losers because the transitions there have to be significant and will be costly. What I'm going to hold off on, and we can address this in a subsequent webinar, is, what are the policy and regulatory implications for these nations that now need to start preparing? So without any further ado, I'm going to say, Axel, thank you so much for the discussion today. And let me recognize the role that I think you'll be playing in this collaborative that Canada is anticipating as the host of this event that you've given us some insight to. So thank you. And I look forward to our next interview within the next couple of weeks.
Thanks, Barry. Appreciate it.
Well, thank you all. And thank you all for joining us. We have a good turnout. We did have some points being made and questions that were being raised. So I'm going to ask Gord.
I was just observing that fusion gives you at the kind of energy output per mass of reactants that they're talking about. It gives you a fantastically high what's called ISP, right? The characteristic of a rocket. So it should make it possible to zoom around the solar system really without too much trouble.
Okay. And I think you also made a point, which is, I think, worth considering, that if we have fusion and we have this form of energy, we may have the means of disposing of radioactive material out into the solar system. But I'll leave that aside. A second point, Jessen, you raised 2 points. One regarding the universities that are forming foundations, I gather in the interest of advocacy or the interest of helping mitigate the long-term implications or the moderate implications. So do we need an infrastructure of NGOs, not just engineering entities and commercial entities, but that third-party NGO infrastructure? Axel, have you given any thought to infrastructure beyond what is typically the supply channel, that advocacy body that helps citizens mitigate the risk?
I think it's really essential for the citizens of Canada and other countries to understand energy much better than we currently understand it, and for them to understand nuclear fission and nuclear fusion much better than we currently understand it. And that's where the not-for-profit sector, organizations like the Fusion Energy Council of Canada and others can really play an important role. That's also where some of the international agencies, like the International Atomic Energy Agency, can play a very important role. So education of the public in the broad sense is essential, because that influences the politics and through the politics, it influences the laws that are being created and the regulations that are being created. And they have to be helpful, and they have to be thoughtful, and they have to be protective of human health and environmental health, all within the context of economic viability.
Dimitar, you talked about an LENR experiment. I'm not familiar with it. I'm going to ask Axel. Actually, are you familiar with the LENR experiment that he's referring to?
Yes, Dimitar and I have had a number of discussions. I've read his reports and papers with interest. I have encouraged him to continue pursue his work, but I've also encouraged him to collaborate with others, including Canadian Nuclear Labs, because they have some facilities that I think would be quite helpful. So I encourage him, as well as others, to do thoughtful experiments and to carry them forward, but to have them validated by others. And one good way of doing that is, of course, to publish results. I know Dimitar has published some of his earlier results that I've seen. I haven't seen anything in the last year or so.
Francis, you phrased the question that we discussed to some extent. Maybe we take a different angle at it, or a different approach regarding timing. What is in the way, and does anyone dare to say it's anything other than 50 years?
I think we will see the demonstration of fusion energy production on a significant scale well within 50 years. I think we can expect to see probably within a decade some significant fusion energy production, not at competitive prices in all likelihood, but we should be able to see that. We will see, I think, the rollout, if we can manage some of these very serious scale-up problems. And when I say serious scale-up problems, if you do something on a small scale, on a laboratory scale, or even on a pilot plant scale, you do not typically encounter problems that you encounter in a plant that might be 100 times or 500 times as large. And those are different kinds of problems. They need to be addressed and solved, and that takes time. So I'm optimistic that we will have fusion energy production within 10 to 20 years. I do not think that we will have a very large number of fusion energy plant even by the middle of the century. But fusion energy will be a technology and in all likelihood produce energy in copious quantities from many plants in the second half of this century. But in order to get there, we have to do the work now. You know, it's not like being in the 1930s and say, I can envisage hundreds of planes flying from the United States and Canada to Europe and Australia. You have to take this step by step. And that's what happened in the aviation industry. That's even what happened in the automobile industry. It took quite a long time from the initial cars to become a commodity, and Henry Ford played an important role. So I see fusion energy production as a technology that will really make major contributions on a very large scale in the second half of this century. But it will show clearer benefits even well before that, but in a much more isolated way. And the question is, for me, whether Canada is going to be one of those sites, and whether Alberta and British Columbia are two of those sites. And I'd like to see that happen. And we can talk about what it takes in order to achieve that.
Someone has posed the question of what needs to be done, and what could Canada do, or what should Canada and or Alberta do in order to position us to be a supplier in this industry?
So At the national level, we do need a strategy that enables us to develop fusion energy technologies. And when I say technologies, I mean not just the fusion reactor technologies, but also the technologies that surround the reactor. And we need to have a strategy to support that work in our public institutions and in academia, in our governmental institutions like Canadian Nuclear Labs, for example, and in the private sector. And we are able to do that because we already have the foundations for it. Now, a very important aspect for Canada is to think about whether Canada should specialize and certain areas that will be important. And one topic that always comes up is, should Canada specialize in tritium production and all matters related to tritium? Because we have already a very major advantage in tritium, since tritium is an undesirable byproduct of the CANDU reactors. By necessity, we had to develop expertise with respect to tritium. But I and many others would argue that we should do more than just focus on tritium, as desirable as that is. You heard us talk about general fusion, which has a particular type of fusion technology that I think is well worthwhile looking at. And then there are very important questions with respect to what's called the fuel cycle. This is the equipment that surrounds the fusion reactor. And let me demonstrate that by means of giving you some simple numbers. In the case of the magnetic confinement approach to fusion, the burn ratio, that is the fuel that goes into the reactor, and the portion that is converted is probably less than 5%. So you've got 5% of your input material being converted into energy and helium, of course, but 95% is not. In the case of the inertial fusion approach, that percentage is higher. It's probably in the range of 30%, but it's still nowhere near 100%. General fusion claims that its approach might be in the range of 50 to 60%. But in all cases, a large portion, a significant portion of your very valuable tritium is not converted into energy. And therefore, you have to recover that tritium in order to be able to recycle it. The same is true for deuterium. And how to do that is a technologically difficult task. The current approach that we take involves electrolysis, it involves oxidation in order to separate the helium, it involves electrolysis, and then it involves cryogenic distillation at close to absolute zero in order to separate the deuterium and the tritium. Is that the right approach to take? The other really important aspect is that the fusion reactors all operate, well, not the general fusion one, but the other reactors all operate at pressures that is almost absolute zero pressure. So it's a complete vacuum. So to get material out of the reactor, in order to be able to separate the helium from the other products that you make and the products that you want to recycle, is technologically very challenging. And what it takes, I think, are basically two things, in addition to finances and resources, of course. It takes ideas and some new ideas, and then it takes current technologies and new technologies that need to be optimized. But you need both. You need the ideas and you need the optimization of either existing ideas or even future ideas.
Axel, one of your features, and the one that I personally have found most positive is that while you have engineering in your background, you and I have talked many times about the social and economic impact of fusion and anticipating its disruptive implications and mitigating those so that we have a not a near backyard mentality and we separate fusion from fission in the understanding of the public. It seems like mankind's curiosity often overwhelms his interest in anticipating these disruptive implications, saying we'll deal with them after the fact. This is massive. This is like the invention of fire. I don't think anybody can understate how significant the arrival of fusion may well be in a world that has been used to using wood, coal, and some fission. This is a massive implications for society at large. Is anybody really paying attention, given the breadth and the depth of what the impact of fusion arrival will be? And some might say, well, it's 50 years away. It may take 50 years to get the infrastructure in place in order to mitigate the risks. You want to share with me the passion that you have about understanding both the social and economic side, not just the engineering and technical side?
Yeah, so I think it's very important to look at the social, economic, and both small p and large p political aspects of any major new technology. I'd like to point out something which should be obvious, and that is that human beings are capable to anticipate the consequences of their actions to a much greater extent than most animals are, or most other biological systems are. So we have the ability to think ahead of what the potential consequences are of actions that we are taking today. But what we don't have such a great ability is, in fact, to act on the insights that we acquire from looking out into the future. And that's what I'd like us to do, particularly with respect to fusion energy. I don't want us to be in Canada in a situation where somehow a select group of people or companies develops this technology and renders it economic and competitive, and then puts out a lot of people in other energy sectors, puts them out of work. I think we need to think about transitioning earlier, and we need to think about transitioning not only in terms of the young people that will enter into the fusion energy sector, but also the people who are currently working, might have worked in coal-fired power plants, or today who are working in natural gas-fired power plants, for example. What can we do in order to enable them to make the transition? And even though we don't know exactly when and how the transition comes about, but I think it's wise to do that. And there's some countries that are really quite good at doing this. The Nordic countries, in particular, Sweden and Finland, are good at it. And we have some isolated, well, we've got some specific examples that I could cite where this kind of transition has taken place smoothly, where people transition from one sector to another. And in this case, we're largely talking about transitioning from one energy sector into another energy sector, but it could also go beyond that.
Well, this is a good point to bring this to a close, as you've just underscored really the whole reason for our interest in all forms of energy, fusion in particular, not just ramifications for the climate, not just ramifications for the economy, but certainly ramifications for the future. Public education, helping the public better understand so we don't have a bunch of Luddites running around as soon as they become aware of what fusion is, that before they really understand its benefits, all we're doing is studying its risks, of which there are very few from what I can see, other than its disruptive implications on existing energy sources. So I'll do one more call to see if there are any hands up. I think we've pretty well covered everything that was in the chat. I know, Mel, you raised the interest of material, the issue of materials science, but I think we've covered on that. that the containment vehicles, and I saw some research come out today that some significant advances have been made in material science that may well show some progress in containment. But I see you've got your hand up. Kevin, I'll call on you first, then Mel, and then I think we'll call it a day. Go ahead, Kevin.
Yeah, so my understanding is that fusion energy can't really be weaponized. If that is the case, that it can't be weaponized, can we safely share and provide the technology to energy poor and fossil dependent jurisdictions without the fear of proliferation?
While it is true that fusion energy cannot be weaponized, and by that we understand can be used for the construction of materials for mass destruction, there are parts of fusion energy production and technologies that can be weaponized. For example, the very production of tritium. Tritium can be used as an enhancer in atomic weapons. So the trade in tritium is tightly controlled. All the tritium that Canada produces in its CANDU reactors is strictly accounted for. It's only sold to customers in Canada and abroad that meet non-proliferation requirements, and that's very strictly adhered to. Similarly, the separation of lithium-6 from lithium-7, which can be viewed as part of the fusion technology supply chain, that technology is possible to weaponize. So we are very careful and very specific in Canada. We have very tight regulations with respect to the dissemination of technology that is needed for fusion energy production, but can potentially be used for the production of weapons of mass destruction.
Any last comments you want to make, Axel?
Well, the main comment I'd like to make is to thank you for your interest. Thank you for having participated in this webinar. I hope we whetted your appetite for the next webinar on the topic. And if you have questions or suggestions, please reach out to me or to some of my colleagues and the Fusion Energy Council of Canada. Perry is, of course, one of them, but I saw Alan Offenberger is here as well. And Alan is kind of the grandfather of fusion energy in Canada, and he's provided wonderful guidance on fusion energy to me and to others. So I thank you for your interest and your participation and look forward to future engagement.